Hello everybody. So what we're going to be looking at today is the first derivative test and also Rolle's theorem and the mean value theorem. And yeah, so let's go ahead and get started. So we're not here all day. So let's see. I guess we'll go ahead and start with Rolle's theorem and the mean value theorem because at least when I did the homework, that's what it started with. So Rolle's theorem is this. Well, let's draw a picture first. So the idea is if you've got a function and let's say at a you're up at a certain value, it doesn't matter what it is. I'm going to draw it at 3. I said 3, that looks more like 4, but whatever. It goes through 2 points. And those 2 points there happens to make a level line. Well, what Rolle's theorem is going to say is that if you've got a function that goes through those 2 points, like I just drew one, sort of, then what happens is there's got to be a point somewhere in between A and B. In this case, it's about here, where if you come up here, the slope is also 0. Right? So if you have 2 points, but the A and the B, where the slope between the 2 points is 0, then there's got to be a point between them where the slope of the function is 0. And that's what Rolle's theorem says, but you know, you have to have certain continuity and differentiability conditions, right? So your function is going to need to be continuous and differentiable, basically. So if f of x is continuous on AB and differentiable on AB, then, oh, and sorry, that's kind of just the boilerplate that's on all these theorems. And then the actual thing we care about is and f of A equals f of B, right? That's what makes them level here at the same level. F of A equals f of B, then there is a C in AB. Let's think about that. I guess I'll do this. I think it's open, but it doesn't matter. There's a C in AB with f prime of C equals f of B minus f of A over B minus A. Let me just change this real quick. There you go. All right, so that's the theorem. And so this is a derivative here. Hold on. This is a slope of a tangent line, which is the red curve that or the red line that I drew up there. Slope of tangent line, because it's a derivative. And this right here is the slope of a secant line, because that is what it is. Oh. No, I lied. Hold on. I wrote the mean value theorem. The derivative 0, right? That's the derivative that I drew. The derivative is 0. It's true though, slope of a secant line. But that particular secant line has a slope of 0. So this is the one that's Rolle's theorem. What I accidentally wrote was the mean value theorem, which is the general version of it. So sorry about that. But slope of the tangent line must be 0. And that's what it shows on the graph, right? This is f prime of C equals 0. All right, so that's Rolle's theorem. And the theorem can be used for proving theorems and things like that. You're not going to be proving theorems in this section. What you're going to be doing in this section is simply going to be verifying the mean value theorem. So like an example would be something like this. I keep saying mean value theorem because it's the same as Rolle's. But so here's what I'll say. I'll say let f of x equal x squared plus 2x. Let me think. Thinking's hard. And it's still one of theirs. Ah, there we go. They say f of x is negative 8x squared minus 64x minus 49. Note f of negative 7 equals f of negative 1, and that is also 7. And then they want to find the value of c. Such that oh, well, no. Just find the value of c guaranteed by Rolle's theorem is all it says. All right, so find the value of c guaranteed by Rolle's theorem. So here is what this says. I don't really care what this function looks like, so I'm not going to do a good job of plotting it. What I am going to do is at least draw these two values in on the graph just to make it clear. So f of negative 7 is, let's see, 1, 2, 3, 4, 5, 6, 7. There's negative 7. Should be up at 7. 1, 2, 3, 4, 5, 6, 7. So here, call it there. And f of negative 1 is also 7, so that's here. Right? And the idea is whatever the curve does, then it's going to have to go through those 2 points. Now I drew it like an upside down parabola because I just looked at this and it looks like an upside down parabola to me, but it didn't matter what it looked like. The point is that if you've got it going through these 2 points where it's at the same y level, right, the y level of 7, then there's got to be somewhere in here where the derivative is 0. That's what Rolle's theorem says, and that's the c that we're looking for. So all you're supposed to do is this. Your only steps are take the derivative, so let's do that. So f prime of x is going to be negative 16x minus 64. All right, that's that. Then you're simply going to set it equal to 0. You could put in a c if you want. You could say set f prime c equals 0 and solve for c. And that's it. So you just go 0 equals negative 16x minus 64 because that's all this is saying here, right? It's just saying set f prime c equal to 0, and what we're going to find is supposed to be a number in between a and b. So we're just going to check that we find this c and that it's in between negative 7 and negative 1. All right, so you move the 64 over. Divide both sides by 16, negative 16. You get x is negative 4. Ooh, hold on. I said we were going to call it c, and I didn't. C, C, C. So I just put c in the derivative and then did all the same work. So that's it. And so this must be at negative 4, which is in between negative 1 and negative 7. And that's all they want. Okay, that's all they want. You just take the derivative, set it equal to 0, and you're supposed to be finding something that happens to be in between a and b. And you're done. Let's do another one. Well, actually, let's write the mean value theorem now because we can do the general version. So the mean value theorem is exactly the same as Rolle's theorem. In fact, when I wrote it down wrong, Rolle's theorem down wrong, it was because I accidentally wrote the mean value theorem. So what the mean value theorem says is you have an A and you have a B, but this time they're not at the same level. They're different y levels. I mean, they don't have to be, but they are. And then you have a curve that goes through them. So there's just a curve that goes through them. And what the mean value theorem says, I can draw this, is that you've got a secant line right here, and the mean value theorem says somewhere in between A and B, there's got to be a place where if you draw the derivative that you actually have the same slope, which that didn't happen there. But that's not what I wanted. Yeah, close enough. Okay, so your f prime of c is going to be the same slope as the slope of the other line. So those are supposed to be parallel if I drew them correctly. And so the theorem is exactly the same as Rolle's theorem when you write it. You still need continuity and differentiability. So if f of x is continuous on a to b, so only continuous functions, and differentiable on a to b this way, so we need the derivative to exist in there, then there is a c in AB with f prime of c equals f of b minus f of a over b minus a. And this time it is what I said it was the first time. This is the slope of the tangent, and this is the slope of the secant, and they're just supposed to be equal to each other. All right, and so that's it. And what are you going to be doing? Exactly the same as that other question we did for Rolle's theorem. We're just going to be doing it for the mean value theorem, but it's the same exact problem really. So here's an example of that. So what value of c, you see it's exactly the same. What value of c in 9 to 64 satisfies the mean value theorem for, they give us a weird function, t of x they call it, equals -4 square root x plus 3. All right, so here is what you have to do. Look at the definition. You've got to write out this. You have to write this out basically, and you know the a and the b, and then you're going to find the c. So what's the a and the b? Well, the a and the b are from your interval. So they have right there the 9 and the 64. So we know the interval is going to give us a is 9, b is 64, right? That's the interval we're talking about. And then we're also going to need the derivative. t prime of x, well, you need to take the derivative of this function. If you're going to take the derivative of the function, you might want to write it this way, negative 4 x to the 1/2 plus 3 for purposes of the power rule. So let's see, the derivative of t is going to be, you're going to bring the power down in front, so you're going to have negative 4 1/2 x to the negative 1/2, and then the derivative of 3 is 0. So you get negative 2 x to the negative 1/2, which is negative 2 over the square root of x. So that's your derivative. All right? So we find the derivative. Now once you have the derivative, you want to, I guess that should have been our first step. Step 1, find the derivative. Right? Step 2, you're going to set up t prime, in this case of c, equals, what is it? Oh, t of b minus t of a over b minus a. So you have to put in your b and your a. So let's do this. So we need t prime of c. So t prime of x is negative 2 over square root x. So t prime of c is negative 2 over square root c. And you can just leave that as x if you want. On the other side, you have other side of the equation, right? You have not that. You have this thing. Well, you need to write that out using this function, okay? And you're going to have to plug in the 9 and you're going to have to plug in the 64. So what that's going to look like is t of b, b is 64. So you're going to have negative 4 square root 64 plus 3. That's your t of b minus t of a, which is going to be, where is it? Negative 4 square root 9 plus 3. And then all of that is going to be over b minus a, which is 64 minus 9. Alright, so you set up that equation, and you just, on the right hand side, it's just numbers. So you just, over here, just work this out. And on the right hand or left hand side, you just leave it. Just leave it for now. So 2 over square root c is what? And you work this all out. So let's see here. We got square root of 64. That's 8. So negative 4 times 8 is negative 32. So you have negative 32 plus 3. And then you've got your square root 9. So that's 3. 3 times 4 is 12. Minus a minus, so that's plus 12. And then minus 3. Over 64 minus 9. 64 minus 9 is 55, right? Yeah. So once you got that, we're just going to solve for c. Which, I mean, I should have done a little bit of work maybe before now, but work out that numerator there. So 3 minus 3 is 0. Negative 32 plus 12 is negative 20 over 55. So we're trying to solve this here. Negative 20 over 55, 5 goes into both of those. 5 goes into negative 20 4 times, and 5 goes into 55 11 times. So let's do that. Then let us go ahead and, you know what, I'm going to cross multiply. I never cross multiply. Let's do that. Cross multiplying is when you have a fraction equals a fraction and you multiply down here to up here, which gives you, in this case, negative 4 square root c. And then you multiply these two, which gives you negative 22, and then you set those equal. So negative 4c square root c equals negative 22. Square root c is going to be 22 over 4, which is 11 over 2. And then square root c is going to be, well, I'm just rewriting that, I guess. Square both sides, c is going to be 11 over 2 squared, which is 121 over 4. And that must be in the interval, or I made a mistake. Right? You can punch that into a calculator and see that it's in between 9 and 64. So what that say? I didn't have a picture, but I draw a picture of it. Not to scale. Oh, these numbers are negative, aren't they? Oh, negative to positive. Okay, hold on. All right. So, what's the function? Okay. So at 9, we're at 9. And at 64, we are at negative 29 or something like that. Negative 29. Not to scale. Don't get mad at me. So what this does is wait, that's not right. Hold on. If you put in a 0, you get 3. Oh, if you put a 9, you get negative 12 plus 3. That should have been negative 9. Oops. Down here. My bad. Alright, so what the curve actually looks like is this. Well, it's hard to draw for me because nothing is to scale. But that's your curve. And what we did was we found the number in here somewhere where if you came down here, you would have the same slope between the two red dots, which I'm not going to draw because it's already taken too long, and there. So like at C, the derivative should be the same as the slope between the two red dots, if we drew it right. I didn't really draw it right. But yeah, you can do it all algebraically. And that is the mean value theorem. It does get used to prove things. And we can't do that. But so you have a couple of these. Pretty much exactly the same problem every time, it looks like. And then what we want to do is we want to look at the first derivative test. First derivative test is easy. Pretty easy. So last time, let's see, first derivative test. Okay, you already know about critical points. All right. You already know about critical points. Right? They are places where they are points on your graph, in the domain of your function, I should say. Points in the domain of your function where the derivative is 0 or undefined. So we've seen those. So like if I draw a graph like this, there's a graph, then there's two critical points on this graph. There's one right here, and then there's one right here, right? That's going to be 0 equals f prime x, critical point. And then this one right here, because of the point, is going to be a f prime undefined, critical point. But both of those occur. And the thing about them is that those are places where you might have a maximum or a minimum. That's the key. So the key behind this is understanding that we know from when we did absolute extrema on a closed domain last time that critical points are locations of maximums or minimums, but not necessarily the absolute maximum and minimum. It could be a local maximum or minimum. So we know critical points are often, not always, but often the location of maximums and minimums, typically local. Maximums and minimums, local extrema. Okay, so we already know that. What the first derivative test does is it lets you figure out which it is, because that's what you want to know. And so the first derivative test says this. Says if x equals c is a critical point, and f prime of x changes sign from plus to minus at x equals c, then f of x has a local maximum at x equals c. Now, we need to draw a picture of this. I'm going to write the other one for the minimum, and then we'll draw the picture. So, if f prime of x changes sign from minus to plus at x equals c, then f of x has a local minimum. All right, now let's look at the picture. Let's just actually look at this picture. This picture is fine. Remember that a positive slope, what's that look like? Positive slope is up to the right, and negative is down and to the left. So if you just label this graph here, right here, the slope is positive, right? And then right here, the slope is negative, and then right here, the slope is positive again. So it goes plus, minus, plus. But the point is that if you have the signs go plus to minus, that means the function was going up and then came down. Well, if it goes up and then comes down, then it must have reached a maximum, right? Goes up, then comes down. So it hit a maximum value. And the other way as well. If you went from minus to plus, that means it was going down, but then it's, oops, why you do that? It was going down, but then it started going up again. Well, if it went down and then started going up, then it must have hit a minimum value. And so that's all the first derivative test is saying, okay? But the way you go about solving problems is, you know, you have to be methodical about it to solve problems using the first derivative test. And if you are, everything will be good. And if you aren't, then everything will be bad. Or at least the problems will. All right, so here's a question. Example. So here's an S of x equals 5 over x. Nope, that one won't work. That wasn't the right kind of problem. Okay, here we go. This will work. Determine the local extrema, right? That means minimums and maximums, for t of x again, weird, negative 3x cubed minus 63 over 2 x squared minus 90x plus 1. Okay? Determine the local extrema. So what you're going to have to do is find critical points. Okay? That's your first step. And we know how to do that from the last section. Find critical points. How do you do that? You're basically going to find the derivative, and you need to know where it's 0 or undefined. So, find derivative. That's your first step for finding a critical point. So t prime of x is, and we just take the derivative here. So 9x squared minus, what's 63 times 2? 126? 126 over 2x minus 90. 126, oh, duh, over 2 is going to be 63 again. All right, there we go. There's your derivative. Now we need to look for places where this is 0 and undefined. So let's look for 0 first. Set equal to 0 and solve for x. So 0 is negative 9x squared minus 63x minus 90. Should factor out a 9 there. Looks like, actually factor out a negative 9 there. That'll be better. You get x squared plus 6. Wait, that's 7, isn't it? 7 times 9 is 63. Is it? Yeah. 7x. And then plus 10, right? Okay. You can go ahead and divide both sides by 9 now, just to drop off that 9. Go ahead and use a calculator to help you with this if you want. It doesn't hurt. And then we're going to factor this, right? We're setting this equal to 0. So we're looking for numbers that multiply to 10 and add up to 7. And I think they are 5 and 7. And then from there, we know that you set each of these individually equal 0. So x plus 2 equals 0. And the other one is x plus 5 equals 0. I shouldn't say and, but these are my two solutions. But it's one or the other one will satisfy the equation. So x is negative 2 or x is negative 5. Those are my critical points. Now for part C, you also need where is the derivative undefined. T prime of x. Where is derivative undefined? Nowhere. Okay, so it doesn't even apply to this problem. A lot of problems it doesn't. Okay, so we have two critical points. Now, we've done exactly this kind of thing before on other problems in the last section, but what we do now is different, because what we need to do now is apply the first derivative test. And the way you go about it is not the way the theorem is written. So this is where you need to pay attention. apply the first derivative test. Here's how you do it. You make a number line. Okay. I'm gonna give myself more room. You make a number line with the critical points on it. All right. So what's your number line look like on this problem? Your number line, you just do this. There's a line. It's a number line. We need to put -2 and -5 on there. So you just go -2, -5. Now at those points, I like to label them as what they are. This is where the derivative was 0. It's called t prime. T prime equals 0, and this one t prime equals 0. Okay? Now what that does is it splits up the number line into 3 sections. There's a section here, there's a section here, and then in between them there's a third section, right? So there's 3 sections on the number line. In this case, this splits the number line into section, and the key is that in each section the derivative does not change sign, because in order to change sign from plus to minus, it would either have to go through 0, but it can't go through 0 because we know exactly where the critical points are already where it goes through 0, or it would have to jump from positive to negative without going through 0, in which case it would be undefined. So the point is it can only change from plus to minus at a critical point. So this splits the number line into sections. The derivative does not change sign in each section. So what that means, that's the background. What you want to actually do is from each section that I drew on my number line, you just plug one x value into f prime, right? So the actual step is plug 1 test x value into the derivative from each section, just to figure out if it's plus or minus in that section. And remember, you only need 1 point per section because you know it can't change sign. So like if I label the sections here just as, like, let's say 1, 2, 3, right? Then I need one x value from section 1. So section 1. I need one x value. What x value am I going to use? It could be anything in this section. So anything to the left of -5. So like I could use like x equals -10, for example. That would be fine. And you plug that into t prime, not t. Okay, so this is different than what we did in the previous section where you were plugging into the original function at some point. So I need t prime -10 or whatever. Where's t prime? Oh, okay. I like this form of the derivative with the 9 factored out, so I'm going to say -9 x squared plus 7x plus 10. -10 squared plus 7, -10 plus 10. Is it like that? X squared plus 7x plus 10. X squared plus 7x plus 10. Yeah, okay. So you punch that into a calculator. Plug that into a calculator. So I've got, let's see, well, -900. I said calculator and not using one. plus 10. All I care about is plus or minus here. So inside here, this is a, well, 100, I'll just do it. 100 minus 70 plus 10 is 40 times negative 9 is negative 360. Point is, negative. That's all you care about, negative. It's negative. So you can come over here to your number line and you just label this entire section as a minus. And then come back and we do the next section. Section 2. An x value between negative 5 and negative 2. What x value? Whatever you want. I'm going to use negative 3. That's in between negative 2 and 5. So you need t prime of negative 3. So that's going to be negative 9, negative 3 squared, plus 7, negative 3, plus 10. So that's negative 9. 9 minus 21 plus 10. So you work that out. 9 minus 21. 9 minus 21 plus 10 is negative 2 times negative 9, 18. Which is positive. So in the next section, it's positive. All right, last section, anything bigger than negative 2. Well, what's bigger than negative 2? Lots of stuff. Any number you want, you can use. So let's use section 3. How about x equals 0? That's bigger than negative 2, right? So we need t prime of 0, which is negative 9, 0 squared plus 7 times 0 plus 10. That's easy. 10 times negative 9 is negative 90, so that's negative. So in the third section, the derivative is negative. Now you have to do this. It doesn't always go minus plus minus, okay? Or plus minus plus. It doesn't always alternate. It could go plus 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 in theory. Well, maybe not plus plus plus, but it could go plus plus minus or minus plus plus. You can get 2 in a row. Can't get 3 in a row, I don't think. All right, so there you go, minus plus minus. But the thing is that that tells you what's going on. Let me cut this out real quick. Duplicate, duplicate. Head down this way. Do not need that. All right, now from there we can interpret our answer. So our interpret the answer. I guess we just want to interpret our chart is what I should say. So how do you do it? Well, remember what this means. Minus to plus means it was going down and then it came up, right? So whenever you see a minus to plus, you know, downward slope, upward slope. And I usually don't draw it like that big. I usually do this. I usually go, it went down and then went up. And then for the other one, I go, oh, it went up and then went down. So minus to plus right there, that means there's a minimum. And plus to minus means it looks like this, means there's a maximum. And that's how I remember the first derivative test. You can go read the first derivative test, but really you should just remember negative slope, negative slope, which again, it won't let me do that, but negative slope, negative slope. It's got to look like that. Not pointy, but you get the idea. So you interpret this, and your interpretation is t of x has a local minimum at x equals negative 5 and a local maximum at x equals minus 2, and that's by the first derivative test. Okay? So that's how you do it. It's all about making that chart. Okay? And yeah, that is that. So I don't have enough time right now to do another one of these before my office hours start in 5 minutes. But I will stop here, and good luck on your homework.